So for the last 2 or so years, Facebook has been working to replace an ailing CF Engine 2 infrastructure with something new and dynamic and exciting and cool. And that thing was built, I'm supposed to stay on the red carpet, sorry. That thing was built on Chef. And what I'd like to talk about today is the paradigms and philosophies and ideas behind the system we built and why we built it the way we did, and why I think it applies to not just a large infrastructure like Facebook has, but to basically any size infrastructure. And my pet peeve at conferences is people who stand up and talk about something without any idea of why they are qualified to talk about that other than where they work, and frankly, where you work doesn't make you qualified to talk about anything. So I'm going to spend one slide and I'm going to give you a little idea on my background in this area, and if at the end of that slide you don't think that I'm the person you want to listen to talk about that stuff, there's food out there, you go get some more breakfast, and I won't be offended. And on that note, before I switch to this slide, every time I've given a version of this talk or any public talk, there's been one very specific Metallica shirt that I've worn. It's my Lucky Speaking shirt. And today I'm not wearing it. And the reason I'm not wearing it is because I'm wearing a Polish Metallica shirt, because I thought it was appropriate. So if this talk goes horribly wrong, it's because I'm not wearing my Lucky shirt. So, my background. I have a background in both configuration management and scale. I've used a lot of configuration management systems in my career. Most of the ones out there I've at least tested in some sense or another. But I've also had the chance to co-write one. At Ticketmaster in the mid-2000s, we didn't want to use CF Engine 2. It was too static for a large dynamic environment, and we wrote something called Spine, which is actually open source. It was an effort of a bunch of people. And it was super dynamic, and it was really cool, and it was back in the days before there was a Puppet or a Chef. And once Spine was able to run all of our systems pretty well, I wrote something called Revision, which would do things like allocate DNS and filer space and VMs and all the things you would need in order to have a system that could run some configuration management. And on the scale side of things, as I said, I worked at Ticketmaster, which had about 4,000 systems when I joined the company, and about 6,000 when I left. That was all run by one team of 4 people, 5 when I left, so pretty decent density. And then I went to Google, where I worked on Gmail, which has lots and lots of systems I can't talk about, of course. And now I work at Facebook, where we also have lots and lots of systems, and I'm actually going to work pretty hard to give you an idea of what I mean by that. But the point here is my entire career has been around scaling configuration management, both in the sense of scaling a specific tool or a group of tools, also scaling the people who use that tool, which I argue is more important. So let's dig in. If we're going to talk about scale, we need to talk about the kinds of scale. And there's more than one kind of scale out there. And so if you're sitting down and you want to scale configuration management, you have to figure out what sort of scale is important to you and what that means to your environment. And to do that, we're going to start with a couple of questions. So one question you may need to ask yourself, depending on your environment, is how many homogeneous systems can I maintain? And if this is the environment that you work in, you have somewhat of a simpler problem than others, and something like Artist or rsync may actually be sufficient for you. And if it's not, IBM wrote a beautiful set of tools called XCAT, which are open source and is very much geared towards this sort of thing. But most of you, I imagine, need to ask how many heterogeneous systems can I maintain? And you know, for most people in this room, it's probably something like this. You work in a production environment, you have web servers and app servers and database servers and cache servers and blah, blah, blah. Or maybe you work in internal IT and you have a mail server and a DNS server and a DHCP server and all of that sort of stuff. Either way around, the point here is that you have a bunch of common stuff, whether that be how you authenticate or what OSs you run. You have a bunch of commonality. And on top of that, you have where each system diverges from that commonality. And the way in which you can leverage that commonality and the way in which you express that delta is going to be a key factor in how you scale. The obvious question most people ask themselves is, how many people do I need? And obviously no one wants to hire one person per server that they have to run. So that's the common question. But the less common question that I think people forget to ask is, can I safely delegate Delta configuration? And we're going to talk about why this is so important. But the short version is, if you can take something that you care less about and give it to somebody who cares more about it, you're both going to be happier and scale better as people. Once you've asked yourselves these sort of basic questions and you have some idea of where you want to scale and how you want to scale, you need a goal if you're going to build a system. And so at Facebook, we decided our goal was that we wanted 4 people to be able to manage hundreds of thousands of heterogeneous systems. And we thought that was a pretty lofty goal. But moreover, we wanted service owners to be able to own and adjust the relevant settings that they cared about. And what do I mean by service owners? At Facebook, it's very common for software engineers to own their own environment. And while mature environments will get what we call production engineering support, which is a more operationally minded team to help support that stuff, that's something that comes along much later for most teams. And so it's more common for a software engineer to be running their own environment. And these people, whether it be a software engineer or a production engineer, need to be able to adjust and own whatever settings they care about. So with a goal in mind, we had to sit down and decide what we were going to need to accomplish this goal. The first thing we need is basic scalable building blocks, what everything is going to be built upon, the basic assumptions that we were going to need. And so what are those? The first one is it had to be a distributed system. If it's not a distributed system and you have, say, an environment of web servers or app servers, and you start scaling, your company takes off, you get a lot more traffic, and you're like, cool, let me go add, let's say, 30 more web servers for the traffic that you're getting. And let's say you're using a configuration management system where all of this work is done in some central place. Well, now you've got 2 problems. Because as you go and you add 50 or 30 or whatever it is more servers, you don't know if your configuration management configuration management system is going to keep up. Now you have to go scale that too. And so now you have a scale problem and your scale problem, and that just sucks. On the other hand, if your configuration management system distributes the work to the clients, as you scale your environment, you scale your configuration management. Much better. And we needed a system that was deterministic. This is my pet peeve. If I run my tool and my tool exits successfully, I damn well better have the system I'm expecting to have. I don't want to have to run it 2 or 3 or 10 or 20 times. Eventual consistency here doesn't fly. We needed an idempotent system. This one's a little bit more obvious. If I tell you, hey, SSH should be installed, that doesn't mean go run yum install SSH every fucking run. It needed to be extensible and tie into internal systems. Obviously, Facebook being a big company, we have internal systems, but as it turns out, every .com I've ever worked in my entire career had some sort of internal system, whether that be a flat text file or a CSV file or a SQLite database, an Excel spreadsheet, whatever it was. You have something that's really useful to leverage from your configuration management system. And we wanted it to be flexible. We have a workflow. We push our web code twice a day. We push our configuration management every 15 minutes. We do code reviews. We run off of head. All these things that make Facebook what it is and give it the culture that it has. Every one of you works at a company that has a culture, that has a way of doing things that makes you successful, that makes you who you are. And you don't want a tool that's going to make you change that for the tool. You want a tool that's going to bend to your workflow. And with these basic scalable building blocks, we also needed something else. The second thing we wanted was configuration as data. And what do I mean by that? Well, if I'm a service owner, and I know a bunch of things, I write a bunch of code, I own an app, and I know some stuff. I may know that I need, say, shared memory for my application, or that I need to be able to respond on a certain VIP, or that I need a certain service running, or I need, host NSCD caching off, or whatever. But what I may not know is how do you configure a system to answer a VIP? Or just because I want to move core files and that happens to exist in syscontrol.conf, I don't know TCP WMEM settings, which happen to be in the same file. I may not know what authentication services to configure or what my netmask should be. So what we wanted was for people to be able to express the bits and pieces of these configs they cared about in simple arrays and hashes, which we could then merge into a larger set of arrays and hashes and render into a config. And in this way, everyone gets to say just the bit and piece they care about. And the third thing we were going to need was flexibility. And I touched on this a minute ago, and we'll come back to the workflow aspect of this, but I want to start with prototyping. Super fast prototyping is really useful. We've all heard that story of somebody coming along to a sysadmin and saying, hey, I need this thing on all of our servers. And, well, when do you need it by? Oh, I need it like yesterday, like right now. We've all had this happen to us or been the person who was doing it. And at Facebook, this is kind of pretty common for us, but even if it's not common for you, even if you push code or configuration every 2 weeks or 4 weeks or 6 weeks or 8 weeks, the reality of it is the faster you can prototype something, the faster you can test it, and the faster you can get it ready to be pushed to production, the faster you get back to doing whatever the fuck else you were doing, which means you scale better as a person, which means you do your job better as a person. We wanted a tool where the internal assumptions of this tool could be changed and could be changed easily. We didn't want to have to fork the tool just to change some assumption. Now, obviously, you're going to pick a tool that maps to your organization as best as possible, but no tool's perfect. I don't care if you write it yourself, you're going to run into a case where this tool's assumptions don't match yours. And we wanted to be able to change those when we ran into those roadblocks and change it without having to fork the tool or rebuild the tool or wait for the vendor to release a new version or any of that stuff. We wanted to be able to change it from plugins or configuration. By the same token, we wanted to be able to extend it in the same way. Who knows what you're going to need tomorrow? Certainly, we don't know what we're going to need tomorrow, and we wanted to be able to add whatever feature we needed, again, without having to fork the tool. So let's get back to workflow. When it comes to flexibility, we had this sort of idea of how we wanted the workflow to work. And we're going to take syscontrol as an example. We wanted to be able to say, hey, we're going to manage at csyscontrol.conf, and we're going to manage as a template. But the interesting part is going to be that somewhere early on in this tool, we'd like to build a set of, like a hash that had all of the most obvious syscontrols, an entry for every syscontrol we've ever cared about, and a value that was good enough for the vast majority of Facebook servers. And then we wanted to provide these defaults to the run and let anyone else who had any say on any given server change that data structure, munge that hash as they see fit, delete values, add values, munge values. And after everybody had their chance to touch this data structure, at the very end of the run, we would take this data structure and render it out as a config file. That was the kind of workflow we were looking for. So then we had to pick a tool. And by now, it's well known that Facebook picked Chef, and I'm not going to go into a whole lot of detail about it, about the picking process, but we did evaluate tons and tons of tools and ended up deciding that we were going to do a head-to-head test with Puppet, Chef, and Spine. So those are the ones we did the deeper dive on, and we picked Chef. And everyone can stand up and talk about their favorite tool and give you a million reasons why it's awesome, and I'm not going to do that because that's fucking boring. But what I am going to talk about is something we didn't like about Chef, a problem we ran into, and how we solved it and why it made us like Chef so very much. So for us, there's this thing called node save. And for those of you who are not familiar with the Chef model, the way Chef works is you run Chef, and it runs this thing called ohai. And ohai does introspection. It figures out what file systems you have mounted, what users are on the system, what routes you have, what kernel modules are loaded, all sorts of stuff. What hardware you have, CPUs, RAM, all that kind of stuff. And it delivers this as a JSON object to Chef, and Chef uses that as the beginning of your node object. And then it does the Chef run, it runs all the cookbooks, which is all the people wanting to configure things. And at the very end, as it's gathered all this data about resources it's changed and all that sort of stuff, it takes this object and it calls a node.save, which takes this entire object, shoves it over the network to the server indexes it for a search, and it's great. And if you're a typical shop and you don't have an in-house inventory management system, voila, now you do. And it's a great inventory management system. It knows what OS you're running, and it knows all sorts of information about file systems and all this stuff, and it's great. But at Facebook, we have an inventory management system. We didn't need or want this. And moreover, we have clusters of upwards of 10 or 15,000 nodes. And we wanted to run Chef every 15 minutes, or even more often. And taking these multi-megabyte objects and shoving them over the network every 15 minutes meant we'd melt our switches. And if we didn't melt our switches, we certainly wouldn't have any bandwidth left over for all those pictures of cats that you guys like to post on Facebook. So we needed a better solution. And we looked at all of the various solutions people had proposed for this, and it came down to disabling ohai plugins, saying, hey, don't tell me about file systems, don't tell me about routes, don't tell me about this. And that just sucks. Right? I want to be able to make intelligent decisions. I want access to all of this data. I just don't need to save it to a server. So I sat down with Adam Jacob, the original author of Chef, and we wrote this thing called Whitelist Node Adders. And it was a cookbook, and cookbooks are like sort of logical groupings of configs for Chef, for those of you who are not familiar with Chef. And what it did was it reopened the Chef node save method. It deleted everything in that object that wasn't whitelisted, and then called the original node save method. And what's really kind of beautiful about this is that whitelist was stored in the node object itself, so that other cookbooks could actually modify it during the run. And now we send less than a kilobyte of data back from each machine to the Chef server, and works really well. It's open source. And I don't want to dig too much into code in this talk, but I wanted to put this up because I think it's worth pointing out that essentially there's 5 lines of code here that make this work. And I'm bending the truth here slightly because the filter function isn't on there, which is like another 20 or 30 lines. But ultimately, we changed this really core assumption of the tool in roughly 5 lines of code. And it's pretty hard to argue that that's not really flexible. And so a bunch of you out there are now cringing in your seat going, oh my God, you monkey patched a tool from its own config. And I get that. And I wouldn't necessarily argue that this is something you should do on a regular basis. Certainly just because you want to roll out Apache doesn't mean you should monkey patch Chef to understand Apache internally. You should use all of the things it provides. But when you need a tool like this, it's incredibly useful. At some point, you're going to hit a roadblock where you need to be able to modify the way a tool thinks. And in fact, we've used this a couple times to work around bugs, to backport things, to actually develop new features that then ops code ended up bringing back into Chef itself. So it's been incredibly useful for us. So let's talk a little bit about the workflow. I touched on it a little bit. We're going to dig in a little bit more here on exactly how Facebook wanted this to all sort of pan out. We wanted to provide an API for anyone, anywhere, and by anyone I mean these service owners, software engineers, production engineers, to be able to extend or add configuration to any system they cared about simply by munging data structures, adding values to hashes and arrays, really simple stuff. We wanted engineers to not have to know what they were building on. So just because I want to add an IP address doesn't mean I should have to know about every networking setting. Just because I want to move core files doesn't mean I have to know about kernel tunable schedules, or kernel scheduler tunables. Engineers should be able to change their systems without fear of changing any other system. I want to make a tweak on a web server, I shouldn't have to worry about breaking a database server, right? Testing has to be easy. If testing is not easy, then people don't test. And if testing is not easy, but you make people test, then they just don't do their fucking job. And that's not good either. So we needed that. There was one other thing we needed, and this is really where this talk, I think, differs from most configuration management talks out there. It's certainly where our usage of Chef changes from most other uses of Chef. And there's no term for this that I know of, so I had to make one up. And I suck at naming, so sorry. I call it moving idempotency up. And what do I mean by that? Well, if you think about the way modern configuration management systems work, Puppet and Chef and so on, they manage records. They manage a cron job, a user entry, maybe a syscontrol, a IP address, whatever. They manage these individual records that exist as part of a larger system. And the problem with that is if I tell my configuration management system, hey, add this cron job, and then later I don't need that cron job anymore and I delete those lines from my config, I now have a bunch of stale cruft all over in my environment, and that sucks. If I image a new machine, it's right, but all my existing machines are wrong. So how do I handle this? Well, I can be that dude who writes a one-off job that SSHs to every box and tries to clean it up. And that's some bullshit there, right? Because some box is not going to be up and you have more cruft and it sucks. I can tell my configuration management system, hey, here's this thing, and if you ever see it, delete it, and that works, except that that's just more fucking cruft that's sitting in my repo instead of on my production boxes, and that's just more suckage. But what if we could be different? What if we could manage the entire concept of cron jobs as a whole, or of syscontrols as a whole, or of users as a whole? And so when we told the configuration management system, hey, we just deleted some lines, all of a sudden everything got cleaned up magically. What would that look like? Well, I know this is probably somewhat hard to read out there. This is a graphical diff from Fabricator, the code review tool we use. On the left-hand side over here, there's a user entry and a cron entry. And on the right here, we're adding action delete and a comment here that says, hey, you should delete this block of code after this and this date. Depending on your environment, that may be a week later or a month later. And that sucks. Right? That's just technical bullshit debt that no one's ever gonna fucking clean up. What would be better is if you could just delete your shit and move on. Right? So how do we get there? What does it look like? Well, we're gonna take a case study. We're gonna look at how we did this in one particular area, and it maps very well to how we did it in almost every area. And we're gonna look at syscontrol. And you might have started to see this pattern. I keep mentioning syscontrol a lot. The reason for that is back in the days of CF Engine 2 at Facebook, we had, I'm not kidding, 151 copies of syscontrol.conf. And the reason we had 151 copies of syscontrol.conf is back way before I was there was like a database version and a web version, right? And some dude came along and he was like, well, I need a internal web server, but I want to move core files. So I'm going to copy syscontrol.conf.web to syscontrol.conf.internal web, and I'm going to change my one line. And you know what he did? He just made 100 or hundreds of lines of stale config. Because all the lines he didn't change, he is not managing. He doesn't care. And they're just going to stay there. They're going to be stale, and they're going to suck. And then somebody else comes along and makes some other internal system, but it's not really a web server, but he needs to change, I don't know, some VM tunable. And so we copy syscontrol.conf.internal web to syscontrol.conf.internal service or whatever. And so it goes. And every time someone makes a copy of this file, they're now making more stale configs, oftentimes copied from other fucking stale configs, and it just all sucks. And if we wanted to say, you know what, here's this legacy thing that we used to downtune, and now we don't want to downtune it anymore, we want to change it everywhere, there was no way to know who cared about what lines in what file, and it was a total nightmare. It was just big clusterfuck. And it was my pet peeve at Facebook, and I was like, I will fix this. So I did. So in our proof of concept, we did this with all of the tools that we did the deep dive on. We looked at how to handle this. And in Chef, we wrote FB syscontrol as a cookbook. And in the attributes file, which is the thing that runs basically as early on as possible, we looked at some of that OHI data, the introspective data, and we came up with this hash of every syscontrol we've ever cared about ever in the history of Facebook. And we came up with like a reasonable default, something that was safe for the vast majority of services. And then in recipes, which is where you say the things you want to manage, we said, hey, we're going to manage etsy-syscontrol.conf. We're going to manage it with this template. And by the way, if the contents of this ever changes, you should run sysctl -p. And then we have a template. So let's look at that template. It's 3 lines of code. And for those of you who don't read Ruby or ERB, we're basically just taking this hash, looping over it, sorting it, and printing key equals value. And as you can see in the bottom here, it looks like a syscontrol file. It's pretty simple. And you may be saying, well, Phil, congratulations, you can write a loop. Why is that fucking special? And you would be right. So let me tell you why that's special. This is why that is special. I can go and give the DBAs their own cookbook, and they can assign 2 values to a variable, to variables, and voila, they're now managing shared memory on their database servers. That's it. They don't have to know how syscontrol works. They don't have to know about every other syscontrol. They don't have to understand a whole lot about Chef. They just need to know they care about that setting, and that setting, and that value, and that value. And when they're done and they go, you know what, we've moved on, the database changed, whatever, blah, blah, we don't need these 2 values anymore. They go in their cookbook, they delete those 2 lines, and they go back to having the Facebook default. And that's awesome. It's super flexible. They didn't have to come and talk to us. They just did it, and it was great. So how does that help us scale? So the database guys now spend 2 minutes writing 2 lines of code, and they go back to making MySQL awesome. Because that's what they do, because they're fucking great at it. They don't have to worry about where syscontrol.conf files are stored or what combinations there are or which one to copy and all that bullshit. And my team has to write a 3-line template and then move on with their life. They don't have to worry about the hundreds and hundreds of combinations of syscontrols that exist out there. So my team gets to go back to making configuration management better and making the OS better and doing whatever else we do, adding tests and infrastructure and stuff. And DBAs go back to managing MySQL. And so each one of us gets to go back to doing the job we're best at and we enjoy, which means as people we scale better, we're doing more awesome stuff. And we're only ever expressing the delta. We have less config, which means we have better heterogeneity. A couple other really quick examples. We have a variable for whether or not you want IPv6. We have a couple node functions that we patch in that'll tell you information about what kind of network you're in, that sort of stuff. Cron works very similarly to syscontrol. You add an entry to a hash, you get a cron job. Guess what happens when you delete those 5 lines from config? Cron job goes away. It's great. It's all a template. DSR is another example. You may or may not have heard of it. It's really common in big web shops. And the idea is your internet traffic comes in from clients, goes through a load balancer to be load balanced to your backends, but you respond directly back out to the internet instead of through a load balancer, under the idea that most people's outbound traffic is bigger than their inbound traffic, so you have to buy less load balancers. And this is great and wonderful and will help you scale if you have lots of traffic. But as you might imagine, the configuration on these backend servers to make this work, a little complicated. What makes it more complicated is that it's different if you're layer 2 adjacent from your load balancer versus not, whether you're v4, v6, whether you're Red Hat based or Debian based, right? There's all these things. And so what happened was if you wanted to add one of these in CFEngine 2 days, you would go and generate a whole shit ton of ifconfig files and then write some really complicated CFEngine code to copy the right ones out. But most people didn't really understand what they were doing, so they copied a bunch of shit from other people, and it was a nightmare. And mostly they just copied things and like changed stuff until it mostly worked, and it caused a lot of outages, and it was horrible. And we thought, well, shit, we have real code now. Certainly we can do this better. So we wrote a function. Function figures it all out for you. So what do people do when they need to support a DSR address on their backend servers? They call a function chef and pass in an IP address, and we do the rest for them. So again, we had to write that function once, so we scale better because we don't ever have to think about this bullshit again. And all the people who want to add VIPs, they only have to know the address they care to answer, and that's it. So everyone scales better. Yay. Let's talk a little bit about our Chef infrastructure. And let's start with a disclaimer of sorts. We use both open source Chef and enterprise Chef. It was very important to us, and me as a open source advocate in particular, but Facebook as a whole certainly, that whatever we did, the community could leverage. And whatever we did could be, not only could the community leverage what we were doing, but we could leverage what their community was doing. And for me, and for a bunch of other people, that came down to being able to say that you could run a Facebook-sized cluster on open source Chef. That was really, really important to us. On the other hand, we knew that features and bug fixes and scalability fixes and stuff would be developed primarily on Enterprise Chef and then merged into open source Chef. And having that early access seemed really important to us. And we also wanted to support what we felt was an awesome company, and we wanted a support contract and all that stuff. So we bought Enterprise Chef. But we actually run a bunch of our our clusters on open source Chef. So I can't emphasize this enough. You can run a Facebook-sized cluster on open source Chef. All right, so let's talk about what we do. Our environment's a little bit wonky. We wanted to treat Chef servers as stateless. We wanted them to be commodity hardware, just like web servers that we could shoot in the fucking head and then come back and it'd be great. That meant a couple of things. It meant we didn't want to use search. It meant that we didn't want to use data bags. If you are relying on data on the server and searching it, then you can't just reimage that box at a moment's notice. We also wanted separate failure domains. We have all these clusters at Facebook, and each one of them has its own independent core services, so like DNS and Yum and that sort of stuff. And if one of those goes down, it should only affect that cluster. It shouldn't affect any other cluster. We use the tiered model in Chef, which is a concept only expressed that way in Enterprise Chef, but you can totally do it in open source Chef. And what it means is you have some front-end servers that run like an API endpoint, and then you have back-end servers that are running what would ideally be stateful machines like that hold Postgres and that sort of data. So let's look at the mile-high view of Facebook. Somebody writes some code, cookbooks, roles, whatever you have in Chef, and they send that off for code review. Now, there's actually a testing component here, which isn't represented, we'll come back to, and it's not important for this point. So you write some code, you send it off for code review. No code at Facebook gets committed without code review, period. End of story. So you got to get a code review. Assuming someone likes your code and likes your test plan and all that stuff and approves your code, and assuming you pass the automated lint, which in this case is Foodriti, you can now commit to Subversion. And you commit straight to head. We do everything on head. And if you go, oh god, they're on Subversion, don't worry, most of us use git svn. So anyway, you commit to Subversion head, and immediately every cluster at Facebook starts making that available to the entire fleet. Immediately, which sounds really scary, and it kind of is, and we'll talk about it. So how does that work? We're going to zoom into one of these clusters here, and this is what a cluster looks like. So we have two backends. Each backend is the same. They're in a warm failover scenario, so both are prepared to serve, but only one is serving. And it runs a little piece of software we open sourced called grocery delivery. And what grocery delivery does is make a checkout of a Subversion or Git repo, and then upload all of the cookbooks and roles in it to localhost. So it makes all those available, those configs available on that machine. And then a minute later, when it runs in cron again, it goes, I was at version 1, 2, 3, 4, 5 in Subversion, or big long git hash in Git, and goes, what's changed? And it'll upload or delete cookbooks and roles every minute as things change by literally watching Git or Subversion logs. It's a pretty simple script. Up until recently, it was written in Bash, in fact. And it runs on both backends. So if a backend falls off the internet for a little while, I don't know, card breaks, rack switch goes down, whatever, who cares? When it comes back, it'll fix itself. It'll catch up. If I reimage one of those boxes, when it comes back, it'll catch itself up. And in this way, both backends are always ready. And in this way, all clusters are always ready. And so as soon as you commit, within a minute, all of your configs are available to the entire world. So as I said, we have these 2 backends, and then we have 3 stateless front ends. Those are all active-active, and they're behind a load balancer, and they just share load. And that's the API endpoint. And then you have our fleet of machines that are running Chef. So the server, as I said, is basically stateless. It technically does have node objects on it and some keys and all that sort of stuff, but we don't persist any of the node data that we're collecting during the run. Again, this comes from the whitelist node adders thing I talked about before. We deleted all before we send it back to the server, so node data is not persistent. We don't use data bags. For those of you who don't know much about Chef, don't worry about it. It's just arbitrary data you can store on a Chef server. Grocery delivery keeps roles and cookbooks in sync. And Chef only knows about the cluster it's in, because again, we have these failure domains, which means that even if we were saving all this data, it wouldn't matter, because you could only search data in your own cluster. Grocery delivery, as I said, runs on every backend every minute. So some of you out there are going, but Phil, I don't get it. If you don't have any persistent data, if you're not using knife to tell the Chef server something specific about these nodes, how the fuck do you figure out what Chef should do on these nodes? And you would be right. So we have 2 systems internally to Facebook. One is an inventory management system. It tells you things like what cluster you're in, what kind of hardware you have, what your IP address should be, what your netmask should be, that sort of stuff. All the basic information about every node. And then we have another internal system that's a node grouping system, so people can put nodes into groups of nodes, and those groups into groups, and so on and so forth. And we wrote an OHI plugin that goes and fetches all the data about the currently running host from both of those systems and makes it available to the entire run. Here I call those systems of record. OHI is tied into both. And from there, we can make every decision we need to make. We may have to extrapolate a bit, but we have all the data we need to eventually make the right decision. The last piece of data, for those of you who know Chef really well, is a run list. The list of cookbooks that need to run and roles that need to run on any given host. It's typically stored on the Chef server. You typically edit it per node on the Chef server, and wow, that doesn't scale. So what we do is we force every node to specify its own run list to the server, which is a totally supported option. And with that, we now have completely stateless Chef servers. There is technically some data on them, but it's all data that will be regenerated if it goes away. So on the client, we have a report handler, and the report handler takes just a little bit of data, the most important critical data for like troubleshooting issues, things like the last exception that was seen, whether or not the run was successful, number of resources we updated, how long the run took, how long since the last run, that sort of stuff. And we shove that into our global monitoring system. It's a small amount of data, and it's something we can do at a global level quite easily. On the server side, it's a little bit more interesting. We have Chef server stats, which we open sourced about a year ago. It's a small little Ruby script that's type and version agnostic. You run it on a Chef server, backend, front end, enterprise Chef, open source Chef, 11, 1, 10, doesn't matter. It'll figure out what data it can pull and pull some data. It's data about errors, it's performance metrics, it's anything it can figure out, and it dumps it out in a JSON object, which you can then shove into whatever monitoring system you would like. As I said, it's open source. Grocery delivery, as I said, syncs all cookbooks and roles, and as of the rewrite last week, it even supports data bags, even though we don't use them. And grocery delivery is both in its old and new version, pluggable and configurable, and both are on our GitHub repo. The question everyone really wants to know, though, is, does it scale? How does it scale? Show me graphs. Show me big numbers. So before I do that, let's talk a little bit about what scale means to Facebook, or at Facebook, I should say. Our clusters are big, really big, between 10 and 15,000 nodes on average. So big clusters. We also have lots of them, and I can't give you an exact number because my lawyers would come and be angry at me. But I will say that we have multiple clusters in a data center, multiple data centers in a region, and multiple regions. So if you do some math, you can come pretty close. We have 15-minute conversions, so we run in Chef every 15 minutes with a 14-minute splay, meaning we sleep for some random amount of time, somewhere between 0 and 14 minutes. And grocery delivery runs every minute, which means we have the, I don't know if this joke will land in Poland, but we have the Domino's Pizza guarantee of all of your configs in all of the world in 30 minutes or less. So now you have an idea of what we're dealing with. Let's talk a little bit about the history of the Chef server. About 2 years ago, the Chef server was a Ruby endpoint, and it talked to CouchDB. And there's Hosted Chef, which is the service they run. There's what was formerly known as Private Chef, now Enterprise Chef, where you got something that was kind of like Hosted Chef, but you got the code and you could run it yourself. And then there's the open source version of the Chef server. And they were all roughly similar. And they were having some scalability issues in Hosted Chef. So they took the 3 busiest endpoints on the API server, and they rewrote them in Erlang. And they had to talk to Postgres. Most of the endpoints were still Ruby and Couch, but the 3 busiest ones were Erlang and Postgres. And it made a huge difference. All of a sudden, all their main scalability issues kind of went away, and that made it into Enterprise Chef. And that's what we were looking at when we started looking at Chef, and that's what I was talking to Topscode about, making sure they finished that rewrite, all the rest of them moved to Erlang, and that all that moved into open source Chef, and so on and so forth. So we were using Private Chef 1.4, something like that, which had the dual personality, right? And we were really early on. We had converted like 1 web server, and we were trying to see if this was going to work. And eventually we got all the configs converted, and we had a machine that had been built by Chef, and CF Engine had never run on it, and it seemed to work. So we made 2 of them, and then 5, and then 10, and then 20, and then 50, and then 100. And eventually we found this cadence of about 600 at a time that we were converting from CF Engine to Chef in 1 cluster. And I noticed something kind of disturbing. Every time I added 600 nodes, I lost more CPU idle on the Chef backend than I did in the last chunk of 600. And that kind of scared me. And when we got to about 4,000 nodes, which is a very small chunk of a cluster, all things considered, I was at about 50% CPU idle on the active backend, and I decided I could not go any further. So I called Adam, and I said, dude, this is not going to work. And he goes, okay, let me call you back. About 2 hours later, I get this call back from Adam, and he says, and I quote, so we can put more thrust on that pig, which, if you've ever met Adam, is the kind of thing Adam says. And he meant that they could make that scale better. He said, but I have a better idea for you. You know how we've been working on getting all of the stuff rewritten to Erlang and Postgres? And I said, yes. And he goes, well, that's kind of mostly code complete. We have a bunch of unit tests. We think it works. How about I get a build to you of that this week? And I said, well, that sounds pretty cool, but how is it going for you with that code in Hosted Chef? And he goes, none of this code is in Hosted Chef. And I said, oh, well, certainly some small customers beta testing it somewhere in a lab, or you're running it somewhere in a lab. And he goes, nope, nobody's ever used this code. And I said, well, okay, so no one's used this code, but you want me to deploy it in production at Facebook and put all my web servers on it? And he goes, yeah, that's exactly what I want you to do, because you're going to have to migrate anyway, and it's just going to be better, trust me. Like, fuck. Fuck it, we're Facebook, let's do it. So 2 days later, Adam shows up at my office with a little monkey head USB stick and this thing that like a ninja team had gone off in a corner and written. And I installed it. And this graph is amazing. So the green line is the standby backend, which we never ended up upgrading for the purposes of comparison. The red line is the CPU idle on the active backend. And the blue line here is the number of nodes, which is sitting at 4,000. So this was steady state when I was like, oh, fuck. And here's where we did the upgrade. And you can see all the nodes went away and came back. We just deleted all the data because we can do that. And what we noticed was that the CPU idle on the active backend then went to 85%. nope, something's wrong here. That's not, it's not possible. They can't be using less CPU than the dude who has no clients. That's clearly wrong. So we checked in some changes, and they appeared on all of the servers. Well, metrics must be wrong. So we did a bunch of work. We looked at all the monitoring stuff, and no, all the metrics were right. So this new software was using less CPU idle with 4,000 nodes checking in every 15 minutes than the old software was with 0 nodes ever checking in ever. And that seemed pretty fucking useful. So once we were satisfied that the world was awesome, I started adding more nodes. And despite the fact that that line there is slanty, it's actually steppy. The graph is zoomed out. We went in chunks of 600 nodes over, I think that's like 6 hours. So we did that, and it's worth pointing out that this was Enterprise Chef, and Enterprise Chef has this role-based access control mechanism. So creating new nodes involves creating all these authentication documents, and it's actually fairly expensive compared to its counterpart in open source Chef. So this was, for all intents and purposes, one of the most difficult things you could ask a Chef server to do. And we went up to 7,000 nodes, which was all the web servers we had in that cluster. And as you can see, the CPU idle dropped to like 72%, and then went back up. And then there was a bunch of synchronization that has to happen as everyone pulls down all of the source and does all the things. It dropped briefly again, and then leveled out at like 79 to 80% CPU idle, which is where the other backend was. So 7,000 nodes checking in every 15 minutes was using only as much CPU idle on this backend as the old software was just sitting fucking idle. So massive improvement. So time moves on, and all of this stuff gets merged with, this was like this pre-beta alpha release, right? All this stuff gets merged into open source Chef, which is what we were kind of hoping for and working towards with Opscode. And so I do a code drop of like Chef 11, the rewrite. And it's open source Chef, and we're really excited about it. And so I go in and I install it, and it kind of works. It actually totally works. And I thought, well, let's see how hard I can push this. So I deleted all the nodes from the server, and I pointed 2 clusters all at the same Chef infrastructure to see what would happen. So what you can see here is same color scheme. Red is CPU idle on the active backend. Blue is number of nodes. And again, we're relatively early on in the migration here, so the numbers are a little lower than what I've been talking about because not everything was migrated. And in fact, we're still only about 96% migrated. But this was about a year ago or so. 9,000 nodes. And over here, we delete all of the nodes. There was a slight bug in the script. We had to run it twice. And we delete all the nodes and point 2 clusters at it. So we go to 17,000 nodes. That's a half hour there. So when it registered all 17,000 nodes in half an hour. CPU idle on the back end only dropped to about 67%. I leveled out. There was some synchronization that happens. It dips again, comes back up. And I know that this looks like it's a point, but it actually leveled off again, zooming out on a graph. It actually leveled out at about 82% for quite a while before we killed the test, deleted all the nodes, and put everything back the way it went. So that's 17,000 nodes checking in every 15 minutes with 80% CPU idle, which is pretty fucking impressive. So the answer is yes, it does scale. Let's talk a little bit about testing. I mentioned before that before you do code review, in theory, you do some sort of testing. And those of you who have been thinking about this may have said to yourself, well, if you always commit to head and you can't commit without a code review, and as soon as you commit, it goes everywhere, how the fuck do you ever test anything? That's a good question. We love testing in prod. It makes us feel good. And ultimately, while depending on your environment, you may need multiple tiers of testing that are not in prod. You don't know what your configuration management code is going to do until you've seen it in prod. So we have multiple-prong approach to testing. We use Foodriti to catch the vast majority of errors, particularly in our world where there's hundreds and hundreds of people checking into the Chef repo at any point in time for their various own cookbooks. And we can't possibly code review every last one of them ourselves. Once people sort of get a hang on it, they take code reviews internally to their own team for their own cookbooks. We need some way of enforcing basic sanity, and Foodriti is that. And it's really, really wonderful for this. We also have started using ChefSpec for unit testing for core cookbooks and critical stuff and anything that's like really complicated. Not so much the 3-line template, but certainly anything that's like transmogrifying data and that sort of stuff. In my previous versions of this talk, the next bullet point was Chef Test. We had this thing called Chef Test. It was one of the only things in my talk that wasn't open source. And It was a really long shell script that wrapped this feature of Enterprise Chef called multi-tenancy. And the idea was you could have what were called orgs, these virtual chef servers. And what this shell script did, it was a massive shell script that called a Python script, that called a Ruby script. It would go and generate one of these virtual chef servers for you. It would take your local repo, and it would upload all of it to this virtual chef server. And then it would go to some machine in production that you had picked and change its chef config to point to your virtual chef server. And this changed the way people did configuration management at Facebook. It was amazing. Compared to CF Engine, which was basically untestable, you could actually see what was going to happen. It was great. Over time, people asked for lots of features, and this shell script that was like 200 lines became hundreds of lines and then thousands of lines. And then the thousands of lines called a Python script over SSH, was called a Ruby script, which was fucking horrible. And it was kind of bad. And then also having more and more people use this one-off Enterprise Chef instance way off to the side was starting to not scale well. And a year ago, when Opscode announced Chef Zero, which is an in-memory chef server, we all kind of thought, maybe that'd be good for chef test. But we had more important things to do. While it was starting to all slow down, it worked. It worked well enough. And we had bigger fires. And so then I had this guy, Marcin, join the team. And Marcin's right over here. He should stand up. Stand up. So Marcin joined the team, and he gets assigned this task to like add some dumb feature to chef test somewhere and to fix a couple bugs. And Marcin looked at the 4,000 line shell script and had the same reaction any of you would have had, which was, fuck, I don't want to touch that thing. And so he went home one night, and he came back on Monday after a weekend, and he had made this prototype of a new version of Chef Test that used Chef Zero. And it was awesome. I mean, it wasn't like kind of ready yet. It was a prototype, but it was fucking awesome. It was fast. It managed your Chef Zero instance. It did all your uploads. It tracked your Git changes. It was fucking great. And so we decided to pivot and have him actually like finish this. And so he cleaned it up and factored it out and made this thing. And then we kind of started getting close to Atmosphere, and we thought, well, shit, if this uses Chef Zero, we can open source it. So once he kind of got this mostly feature complete, him and I worked together to factor out the Facebook-specific bits into a plugin and make it all pluggable and that sort of stuff. But it's his baby and his code, and it's awesome. And if you get a chance to talk to Marcin, you should, because it's fucking great. And so we were like, okay, well, we need to open source it, which means we need a cutesy name, so Taste Tester. So let's look at that. What does it do? Ultimately, it manages a local Chef Zero instance. So you're on Taste Tester, sorry, and it fires up this in-memory Chef instance on wherever you are, your dev server, your desktop, whatever. And then it uploads all of your cookbooks and roles, and it even supports data bags now, to this local instance, and then it goes out to some machine in production and points it back to your Chef Zero instance, and you can run Chef on it. And then when you're like, oh, I fucked up, and you change another file, you go, hey, just sync my stuff, and it'll upload whatever's changed. It's really smart. It's super pluggable. When we factored out our stuff, we factored a lot of different hook points into it, so you should be able to hook kind of any crazy shit you want to do into it. It's got a config file. It's pretty awesome. So how does it work? So somewhere on your desktop or dev server, whatever you got, you're on Taste Tester, and then you tell it you want to test, and you go to server, and it does all the things I just mentioned, starts up the instance, does all the syncing. Then you log into that machine, and you run Chef. And guess what? You get to see exactly what your code's going to do in production. Exactly, because that fucking box is in production. And then Chef probably crashes because we all suck and humans are bad at things. And so you go back to your desktop and you VI some files and you fix your bug where you left off a comma or whatever. And you run Taste Tester upload, and it goes, cool. I will upload or delete whatever's changed, and it tracks all that stuff for you in the same way that grocery delivery does. And of course, it's open source because open source rules. So on the topic of source, let's talk a little bit about our source. Chef Server Stats, as I said, has been open source for about a year. It's Ruby. It's awesome. It's version and type agnostic. Taste Tester is the rewrite of Chef Test in Ruby. Very awesome. Thanks to Marcin. Grocery delivery is rewritten as well using the same infrastructure that Marcin wrote. And it's was entirely rewritten in Ruby and also checked in recently. Between meals, we factored out all of this code that was doing all this Git tracking stuff because both grocery delivery and Taste Tester needed it. And so that's a Ruby library that does all that crap for you. So those three things were the better part of the last probably 2 months of our lives, and it all landed Wednesday in the code repo, and this is the announcement, just for you. So in addition to that, every time I give a version of this talk, somebody comes up to me afterwards and goes, so you have all this code in your slides for like these cookbooks, where can I download those? And my answer is always, I don't know, copy and paste from my slides? I don't know. Which is a shitty answer, and I'm a shitty person for it, so I decided to be better. And now we've open sourced FB-cron and FB syscontrol. I had to clean them up a bit. They should work-ish. They're mostly meant as an example. I don't expect them to be dropping sort of replacements, but they should give you actual code you can go and play with and kind of figure out how the model that we're using. And then the other thing people ask me when I give this talk is there some sort of text version that's not slides or a YouTube video where I can like get the core ideas that you were trying to get into my head? And the answer was always no, and now the answer is yes. So all of this landed Wednesday and is all there for you, and we're still hacking on it. And we encourage you to go look at it and give us feedback. And coming soon, so Taste Tester between meals and grocery delivery are moving really fast right now because we're just pushing them into production and finding bugs and needing features and all that sort of stuff. So for the moment, they're all in one repo, and they use require relative and all that stuff. And once they kind of settle down a little bit, we'll factor them out into their own repos and build Ruby gems, and that'll come soon, and it'll all be awesome. But in the meantime, you can git clone that repo and just run them, and it'll totally fucking work, maybe. So what did we learn? We've learned some things. I hope we've learned some things. We learned some things. Maybe you learned some things. Idempotent systems, awesome. Way better than idempotent records, or at least I think so. Delegating delta configuration leads to better heterogeneity. It just does. When you're only expressing the little bits that are different, you're expressing less things. Less things is better. We're humans. We have limited capacity in our tiny little brains. Full programming languages are better than restrictive DSLs. Those of you who've played with CF Engine 2 know that you can't write a loop. That makes me sad. Scales more than just number of clients. I talk to people about this all the time. People are like, well, but this other thing, I can get more than this number of nodes to connect to this. I don't fucking care, right? Buying another computer is cheap. Buying another person is expensive. Less people that have to be there to hold all the config in your head, that's scale. Easy abstractions are critical. Think about the difference between calling add DSR, VIP, or whatever I call the function in an IP address versus generating a bunch of if config files. Abstractions are great. Testing against real systems is useful and necessary. Obviously, if you go to bank, your first line of testing is probably not going to be taste tester. However, actually seeing what something is going to do in production is the only way you know what it's actually going to do. I don't care how good your testing environment is. That should be a step somewhere in your pipeline. So in summary, we asked all these questions at the beginning of the talk, and let's see how we measure it up. I asked, how many homogeneous systems can I maintain? We saw a graph where I was doing 17,000 heterogeneous systems and had a lot of room to grow. We're only using, what, like 82 or 85% CPU idle, whatever the graph was. And since heterogeneous systems are more computationally expensive to run than homogeneous systems, we know we can do even better than that. So the first number is way, way more than 17,000. I don't know what it is. Which answers our questions for heterogeneous systems, something more than 17,000. How many people are needed? My team's technically now 5 people, but that's new. It's been 4 people for a very, very long time. Can we safely delegate delta configuration? Yeah, if anyone can assign to a variable. I want to say thanks to a bunch of people. At OpsCode, Adam Jacob has been just the greatest ally I could ever wish to ask for. Chris Brown, who's no longer there but was very awesome. Stephen Dana, the entire Urchef and Bifrost teams are just fucking great. Andrew Kump, who wrote Food Critic, I can't imagine delegating all of that stuff without some sort of sanity checking, so thank you, Andrew. Everyone I have worked with and do work with and will work with, Aaron, Bethany, David, Casey, Larry, Martin, Pedro, and Tyler. And that's all I got.